It's October the 24th, 2019, and we're at Embry-Riddle Aeronautical University in Prescott, Arizona, and we have Professor Emeritus Eric Becklin, Professor Emeritus of UCLA, and we're going to spend a few minutes talking about the Galactic Center, and in particular about how Professor Becklin has exploited the advancement in telescope technology and instrumentation to, first of all, determine the location of the galactic center, and then leading up to the present day, where using large aperture telescopes, we're able to measure the orbits of individual stars around the black hole and therefore determine the black hole mass. So Eric, let's begin by talking about what we can see in the visible, which is very little apparently, because the galactic center is behind about, was it 25 magnitudes of visual extinction?
Yeah, 25 magnitudes of visual extinction, which means a factor of 10 billion reduction in the number of photons that you're collecting relative to what's actually emitted. So we see a very, very small fraction in the visible, obviously.
So when we look at external galaxies, the nuclei are usually the very brightest things in the visible, but it turns out that for our own galactic center, it's actually ridiculously faint, and it's inconspicuous. When you look at the Milky Way, you couldn't really tell where the galactic center is. So can you explain to us how you got around that problem?
Yeah, well, that was a problem for astronomers for a long time, that they saw the external galaxies when they finally had them nailed down, but our galaxy didn't have a point where it was bright in the visible. The problem was dust between us and the galactic center, and I think that was recognized by a lot of people. And getting around that meant you had to work at a wavelength that could see through the dust.
Yes.
There are a few that can do that, the radio and the infrared in particular, where I was working at the time as a young graduate student. And this problem was posed by my thesis advisor, one of my sub-thesis advisor, Bob Layton. Why don't we see the galactic center in the 2-micron sky survey? And so I started wondering why maybe we can do it another way. And the trick to finding it was first to have a big enough beam on the sky so you didn't miss it, and the other was to have the right position to look at. Now that, you never know, but there was a radio source, SAG-A, that was near the dynamical center of the galaxy. So it was the most likely place where the galactic center was. At least that seemed to be very reasonable. And so once we got the instrumentation together, I decided to give it a try. I asked my advisor, Gary Neugebauer, whether I should do this or not. And he said, no, don't bother, because we already tried with the sky survey and it wasn't there. Turned out they had the wrong coordinate. Or they had the right coordinate, but they had the wrong equinox of the coordinate they were dealing with. So kind of mind-boggling, but you had to do everything by hand in those days. This was back in 1965, 66. So I did a little calculation. I thought we should see it, so I took the equipment with a student up, even though Gary Neugebauer thought it was a waste of time, and put the instrument on the telescope, got it working, and the galactic center was setting because it was in August, but we set it up, made sure things were working, made the first scan at the position I thought it was, and sure enough, the signal went up, and then it went down on the other side. And I knew right away, we had seen the galactic center where all the stars are that you see in M31 and other galaxies. It was a very exciting time.
Marvelous, marvelous. That was great. Okay, so can you describe what happened after that? So what I'm really interested in is what was the next advancement in telescope technology and instrumentation, and how did you employ that to learn more about the galactic center?
The next advance in instrumentation that I was involved in was with the telescopes in Hawaii. And at that time, we were starting to get more sensitive detectors and better pointing telescopes, so we could cover more of an area. But the real advances came when we finally had not just one pixel on the sky, but a whole array. And we had a 32 by 32 array, which is small relative to our cameras today, which have millions of pixels. This one had 1,000 or billion pixels, some of them have. And we started using the camera to see the galactic center, and of course we did see it. We saw it better than what we could do with the single. And we started seeing individual stars. That prompted Don Hall to point out, and we were both thinking there was a black hole there. Other galaxies had black holes, and even some of the gas measurements indicated there was a black hole. Pointed out that we really needed to get the orbits of those black holes.
Stars.
Pardon?
Get the orbits of the stars.
Sorry.
Yeah.
Yes. Thank you. We really needed to get the orbits of the stars that were around where the black hole might be and see if we could actually see them moving. You can do a little simple calculation. Most of the black holes that were known about were 1 million to 1 billion solar masses. And at the distances we were getting into the galactic center, in a year or two, you could actually see the motion of those stars if you got everything right. So I first tried it with my student, Doug Simons, on the IRTF, but the images were not good enough. The real breakthrough came when two things happened all at once. One, bigger telescopes, and the bigger telescope has more collecting area, therefore you have more photons. The other thing it has is it has the potential of having bigger images. Now, if you're limited by the blurring in the atmosphere, then it's all the same. But if you use techniques like what was first done was called speckle interferometry. You did fast exposures in the infrared, froze the scene, and you would find that there were spots on bright stars. You would pick that brightest spot as being the biggest speckle, and then you would just shift and add on that. Well, we did this with the Keck when it first came on board, actually only a year or two later, 1995. And to our surprise, we got some really fantastic images. Now, we didn't see it at the telescope. All we knew at the telescope is we had a lot of speckles on the bright stars that are there, but we didn't know about the stars that were around the black hole. At that point, the radio astronomers pretty well knew where the radio source was that most people thought was the black hole, and it was near the very peak of what we had found earlier for the stars. Not right on it, but very close. Well, it just turned out that our peak was the brightest stars, which were some bright stars, which was good because we could use those to determine the speckles. Adding them up, we got just a fabulous image with 50 milliarc seconds. That's, normally when you do imaging at Mauna Kea, it was 1 arc second, maybe half an arc second. But here we were at 50 milliarc seconds on, just uncharted territory. Well, it was fantastic. The first year, we had our very best data. We kept with that encouragement, and by the way, this was all done with a combination of 3 professors, myself, having worked on the Galactic Center a lot, Mark Morris, who did a lot of work in the radio on the Galactic Center. We were both at UCLA, and then we hired Andrea Ghez. Now, Andrea Ghez has not worked on the Galactic Center, but she knew how to do spectral interferometry. She did that for her thesis at Caltech. So we convinced her to try this. Didn't take much convincing, because Neugebauer was her advisor, and he knew about the Galactic Center. But anyway, it was spectacular, the images. So, but 1 year doesn't tell you anything. You have to then go to the next year and even the third year. So we did the 3 years. And at that point, we started seeing motion of a number of stars that was just obvious that it was, the speed was such that there was nothing else that would cause that speed other than a supermassive object. And we could even determine the mass at that of 4 million solar masses. So that was the start. We went on to improve the instrumentation so that we could actually not have to just use the speckles, which was very slow, and you took time to read out the array, so it was inefficient. Adaptive optics, especially using lasers, allowed us to take images with continuous integration with about the same resolution of about 50 milliarc seconds. Now, it wasn't perfect at the beginning, but the longer wavelengths that you went, and we got an image at 3.7 microns that almost looked like it was the deepest thing you had ever seen, and it was at the time of the Galactic Center. So we then started getting measurements that showed curvature of the orbits. So that gave us accelerations. That pointed back to the black hole, because when anything is orbiting around it, the force is always along the line to the object, so it points right at the black hole. And we also were able to see the emission coming from Sag star. It was a different color. We were getting colors at different wavelengths, 1.6, 2.2, 3.7 microns. And that coming from the black hole was much redder. So we could actually see this object, and it wasn't there all the time. It was coming up and down. So we had not only located that there was a black hole there, we determined that we could measure the radiation from this variable source. Now, it's not the black hole it's emitting, because a black hole, all the photons go in, as everybody knows. All the matter, once it goes beyond the event horizon. So what we were seeing was something associated with a disk of dust and gas that was orbiting around the black hole.